Hello everyone. In this video we are going to look at another topic in the introductory part to adaptive control, and that is self-tuning controllers, or STC. And before I start, I need to mention that the texts and equations are taken from Applied Nonlinear Control by Slotin and Lee. This is a very amazing book. So, what is STC? It's a controller that tries to perform simultaneous identification of the unknown plant. So that's basically adaptive control, right? Not only you're trying to drive the tracking error to zero, you also try to identify and find the values of the unknown parameters in the plant. Now, I need to mention that if you do estimate the unknown parameters of the plant offline or ahead of time, for instance, using techniques that you have in system identification, for instance, for a linear system, list the squares, right? Then once you find these parameters ahead of time and then apply those parameters in the controller, that is called indirect adaptive control. That is not what we're going to discuss in these lectures. To identify the system parameters ahead of time, and then assuming that you know them well, you apply them in a control. Here we try to do this parameter estimation and the control at the same time, okay? And there are different topics that we're gonna see. I'm gonna talk about self-tuning controller in this video, and in the next one we're gonna talk about MRAC, which is model reference adaptive control, okay? So we're going to see these different ways to do this simultaneous estimation and control. So what would you do in this STC? To give you an example, again, let's focus on the simple example of a simple mass, and you can control the force applied to it through your control signal, and the goal is to make the position of this mass to converge to some desired position xt, or the difference between them x tilde to converge to zero. Now pay attention, in this video I'm defining x tilde the opposite of what I did in the previous video. Here x tilde is x minus xt, not xt minus x. In many control books, as I said, when they define the tracking error, they go actual basically state minus desired state instead of the other way around. And what that one does is, in this control law that we had last time, which was PD plus fit forward, or you might also call it pole placement for a linear system. Last time, if you remember, we had these two to be positive signs, positive KDX tilde dot, positive KPX tilde. This time, since we changed the positive negative that we had last time, we also have to change these two positives into negatives. But it's essentially the same thing, okay? So the equation of motion is mx double dot plus u. This m is what we don't know, and instead we use its estimate m hat, and we use the PD plus fit forward control law with the estimated mass, right? We want this tracking error x tilde to converge to zero. And the question is, how would you come up with this estimate of mass such that this error goes to zero, and hopefully this m hat also converges to what? To the actual m, okay? So, last time, if you remember, I gave you a parameter update law, and I did not explain where that comes from. Remember, when I showed you this control law, if I go back, it was this one, okay? We did not explain where that one comes from. So in this video, I want to, when I give you a parameter adaptation law, I want you to know where that comes from, okay? So we want to explain that in this video for this category of adaptive controllers called STC. So where do we get our law? So you say, well, let's assume that you have an accelerometer and you can measure this acceleration x double dot. If I can measure the x double dot for a given u, so I know my u, and this one I can measure with an accelerometer all I need for the m is to divide that u by x double dot, and that gives me a good estimate of m. As simple as that. Why do you need to do anything else? It's a linear relation, 1-to-1. Make the input u 2 times bigger. Ideally, acceleration should be 2 times bigger. And if you can plot this u versus x double dot, right, then probably the slope is m hat. What's so hard about it? The hard thing is this. First of all, these accelerometers, these measurements of accelerometers are not some constant, beautiful single number. Okay, if you ever looked at accelerometer measurements, they are very noisy. Even if the signal is supposed to be constant, they are not. You're going to see a lot of variations and noise in it. Second of all, if this acceleration is very small and the input that you're trying to pass to the mass, the external force, is small and acceleration is small, right? Then you are dividing by some small number, and this estimate might not be very accurate. So instead of doing this, we try to cross multiply and say, well, let's keep u as m hat times x double dot, right? And instead of writing it as equality, you write it like this. You say this difference should be equal to 0, right? You write it like that. Ideally, if I know my exact m hat and I have not super noisy measurement of x double dot, this should be equal to 0, but I know that I don't have my m hat and I don't have my x double dot as perfectly good signals, so I would never get this right hand side to be 0. Instead, I would get it to be some residual term. We call it E, error, okay? And the goal is to find this m hat so that we minimize this error for different measurements of x double dot and u. In order to do that, we can simply square both sides, right? And then find this m hat that minimizes this e. And since it's a function of time, we minimize the error squared over time integrated, the integral of the error. And so we have to use a linear square, least square technique. So here, as I said, E, the definition of it is m hat x double dot minus u. And as you know from your simple list of squares, the solution to that, if this is E, the solution to that is going to be what? M hat equals integral of wu dr over integral of w squared dr, where w here is the same as what? The acceleration. We can say w is the measured acceleration, right? So in this case, E is basically what? M hat w minus u, and it's very easy to show because J, as I said, is going to be the integral of m hat w minus u squared, right? And we try to minimize j with respect to m hat, so partial of j with respect to m hat should be equal to 0. Clearly, you can see that this is going to be 2w times m hat w minus u equals 0. And from here, the only thing is the integral doesn't go away, so the integral is still there. So if you do it and get rid of these 2, you see that the integral of m hat w squared dr or dt equals the integral of what? If you multiply w by u, right? Or w u dr. Okay, and if you assume this m hat can be taken out of this integral and it's constant, then clearly it's going to be the right hand side divided by the left hand side, which is exactly what you have over here, right? So this is my least squares estimate for what? For m hat. Good. If I know some input signals and I can measure the acceleration for them using the accelerometer. Now, this is good, and you have to do this integration once for numerator and denominator, and that gives you m hat. The problem is, if your m hat, this is m hat, not m, if your m, or m actually, yes, because if m changes, that means m hat has to change. If your parameter of the system m, if this mass does change, for instance, let's say your mass is carrying, your cart here is carrying some object, right? Like for instance, what? It's a dump truck or something. And as it moves, it has this gate here, and those sands or whatever gravel, they fall off, so this mass is over time changing, reduced, right? For instance. Or it is carrying some object, and like for instance, the trucks that you see in farms, and the combine machine is pouring all those flour or everything in them, so the mass is increasing. So if that's the case, then this integrals in numerator and denominator, they have to be done in every time step, and using that you have to what? Keep updating your m hats by calculating numerator and denominator integrals. So instead of doing it this way, using this integral thing, it's better to do it using a differential equation or a recursive equation, where you can gradually change this m hat. So instead of having one formula for m hat, you better have some formula for m hat dot. So you can update what? M hat, or you can change the rate of change of m hat. How do you do that? This is the derivation part that I promised you. So you say, well, here we define this denominator, right? 1 over the denominator, this part. This can be written as that times 1 over denominator. This 1 over denominator, I call it P, if you don't mind. Then my m hat estimate is going to be P times the numerator, integral of WU. Correct? Now, I take a time derivative, which is what I want. So here I take a time derivative, and m hat dot is going to be here. This is a product. It's a times b. So it's going to be p dot times the integral plus p times derivative of integral. Since this integral is with respect to time, derivative and time integral would cancel. So you get the integrand, which is what? U times w, and of course times p. Okay, so that is m hat dot. Now we need to simplify this parameter update equation. How? From relation 3, if you look at relation 3, m hat is, as we said, this numerator times what? Times p. Look here. So from here, if I say what is this numerator can be written as m hat over p. So here I'm going to replace that by m hat over p. And the other thing I need to replace is this p dot term. Where does p dot come from? Well, that comes from the definition of p. If you look, p is 1 over that integral. If I take a reciprocal from this, then 1 over p is the integral of w squared. Now take a time derivative. You know, the time derivative of 1 over p is negative p dot over p squared. And the integral of the time derivative of integral of w squared is simply w squared. So cross multiply, you get p dot to be negative p squared w squared. So this should be negative p squared what? W squared. So if you plug them in, you get this for m hat dot. Now here 1p and 1p would cancel. You get the simple p term, you get the w term, and you get the m hat term with the negative sign. And if between these two terms you see there is a p and there is a w common in both of them, so I factor it out with a negative sign. If that's the case, then from the first term a w and m hat would remain. From the second term, the u with a negative sign would remain. And what is this guy here inside the parentheses? M hat w minus u. If we go back, that is the definition of what? That is the definition of the error. Which error? This is not the tracking error. The tracking error was called x tilde. That's not this error. It's the error between what? Input, output of the system, right? U was input of the system, output is, really m hat x double dot, right? And E is the difference between them. So E here is the least squares error, not the tracking error. So if I have that and plug it in, my m hat is finally going to be what? Negative PWE, where W again was what? Was your measured acceleration. E is the least square error between m hat, what? W minus U that you give to the system, and P was basically 1 over P was integral of, as you can see, W squared, so P was 1 over integral of W squared dr from 0 to T. Yeah? And this U, if you remember, it was what? It was m hat times x desired double dot minus kd times x tilde dot minus kp times x tilde, and x tilde was x minus x desired. So if I can plug these equations, I should be what? Good to go. But first thing is I need to incorporate this. This is a first order differential equation, which gives me P. Once I have P from here, I'm going to plug it into this. And this, once you integrate this m hat dot, that is going to give me m hat. And m hat can be used in the control. Yeah, and then ideally, once you pass this, your error should converge to what? To 0. So here you see that the adaptation law m hat equal negative PWE is derived for you. And to show that it is effective and it is working, I made you a Simulink file using the same thing. And my desired position is, again, a sine function. And I need the desired velocities and accelerations, so which are cosine and negative sine. I pass them to my STC block. And here I don't really have an accelerometer. So the way that I get the acceleration was I get my x dot. I use the time derivative block, and to make it more realistic, I added some band limited white noise with the noise power. So here my acceleration W that I measure is not going to be a clean signal. If you look here, you clearly can see that it has what? It has noise in it, right? And if you look at it in a closer look, as I just showed you, you clearly see that it's not that clean, beautiful acceleration that you expected. Okay, and you can make the noise even harsher. But with this level of noise, you're going to see that my system is capable of tracking the harmonic signal. So let's go ahead and see what I have. The actual mass of the system is 1 kilogram, as you can see, but when I start estimating my m hat, you see in the initial condition, I consider it to be 0.7 kilogram. Okay, so I'm 30% off for my mass estimate. Still, I can show you that the system is working. So what did I do here? I brought in x dot and xd dot, subtracted to get x tilde dot. I brought x and xd, subtracted to get x tilde. The kp and kd I chose was 8 squared and 2 times 8. Then negative kd x tilde dot, negative kp x tilde plus xd double dot is the signal that when I multiply it by m hat, that is the u that I'm going to send to the system. Now, this w, which is that noisy acceleration, I bring this w, multiply it by m hat, and subtract it from the u that I'm sending to the system. That is going to be this e. Which e? This is the e of the least squares. Not the tracking error. That's not x tilde. This is the least square error. How did I get my m hat? Well, I integrated m hat dot. What was m hat dot? If you remember, it was negative PWE. So I need this w, made it negative w. I got P, and, right, that's P, and I also got this E. So here I'm multiplying all three, negative W, P, and E. So that is m hat dot. How did I get P? I went from this equation, that P dot is negative P squared W squared. So if you look here, this is P dot. Clearly it's what? Negative P squared. So I got the feedback from P, squared it, made it negative P squared. And then this W, I made it square. So this is what? Negative P squared W squared, which is P dot. And for my initial P, I just plugged in 1, okay? You can change that number. It's not going to change anything. And I ran the system for 20 seconds. And here you can see the tracking error. Let me show you. Look, your initial, even your initial condition is not the same as your desired initial condition. So your desired initial condition starts from 0. Remember, it's a sine function. Here I'm starting my initial x at 0.5. Okay, so I'm not starting right at the desired. And you can see that very fast my system is what? Able to converge to the desired position, right? And as I said, this is my noisy acceleration. Clearly you see the system does have a noise. And this is the m hat, the estimate of the mass that I started at 0.7. And as you can see, it is what? Gradually converging to 1, okay? It has not converged to 1. It takes quite a bit some time for it to converge to 1. But you see already it is at 0.95. And it is gradually, as you can see the slope, it is going to converge to 1. Okay? You can change those gains here. But those gains, only what those gains do is they're going to affect how fast your x converges to x tilde, not how fast your m hat is converging to actual m. Okay, you might say, what about this initial condition? Can I change this initial condition? If I make this initial condition 10 instead of 1, would that change anything? Let's take a look. So here, first make sure, you see the error is converging and to 0. And you see now, if you look, for the same amount of time, your m hat is now past 0.97. So yes, it does affect. Now this slope is not as big as last time, but the overall level is up. And why is that? Because if you look at the definition of P is the integral of 1 over acceleration squared. So P at 0 is when this T is 0. And integral from 0 to 0 of a signal is basically what? 0, right? So ideally, P in the beginning should be a big value, 1 over some very small number, initial acceleration. Okay? And it might be to increase this P in the beginning, but again, it's not going to make the m hat to perfectly go to 1, even over 20 seconds, but it can change the effect of m hat. What really you care about is this part, that you can follow the desired trajectory. Okay, and you might say, if I make my noise a little bit harsher, right, so that is too much noise, can you still converge? So let's take a look, see. Yeah, you see, you still can do it. And now if you look at the noise, the signal is not really a good signal. Look at that. It's clearly the acceleration really contaminated with noise. Okay, and it is working, and your m hat is now not doing the great job as last time. Okay, seems like it's even reducing a little bit. Not only it dropped from 0.95, it is going a little bit down. Okay, so that is another thing, that least squares is doing a good job, but then you have too much noise. The estimate of least squares is not perfect either. So hopefully this video gave you an introduction into let's put it at 5, and I published this file, give you the download link under video description. So you learn some basics about this category of adaptive control called self-tuning control. And as I said, in the next video, we're going to talk about MRAC MRAS, and the MIT rule. So hopefully it was useful to you all. I'll see you in the next lecture. Thank you.